Welcome back. This is lecture number 31. In this lecture, we are going to talk about small signal modeling with closed current loop. Now, we want to extend the equivalent circuit concept which we have learned from an open loop DC-DC converter, and we want to extend this for current mode control when the inner current loop is closed, because we have still we will not consider in this lecture with the closed voltage loop, that we will discuss in the subsequent lecture. So, modeling of current mode control, then circuit average technique is used to derive equivalent circuit model, and I will show you that it will be a first order approximate model, and then we will derive small signal model, first order model under current mode control. We will derive various transfer function and we want to understand their significance. Then we will say at the end whether this first order model, we want to open up some question, and in subsequent lecture we will see whether this first order model is really good enough, can we really use it, or where is the limit. So, all this will be covered in the subsequent lecture, but today we will start with the very basic modeling approach. Few more things I want to emphasize before we start. We talk about right half plane 0 in a boost converter, and we also saw that the location of right half plane 0, what is the expression. Now, we also we are interested to see, and in a boost converter under open loop, we saw there was, for an ideal boost converter, there was one RHP 0 and 2 poles. For a practical boost converter, there is one more 0 due to ESR. Now, in current mode control, we want to see whether the boost converter under current mode control, do you have a right half plane 0, and if you have, whether the location will be same as earlier or it will be different. That aspect also we will keep in mind. Okay. The another aspect we will see in current mode control, a load regulation aspect, that also we will keep in mind, because in earlier lecture we saw current mode control offer excellent line transient response. So, there is no problem with the line regulation, but we want to investigate what is the aspect of load regulation in current mode control. So, a current mode control block diagram we have discussed earlier, where we will sense the output voltage here, and it is compared with the reference voltage, and this is our error voltage. It will go through a controller, and the controller will generate the current reference. So, we will use different notation, sometimes we will use IREF, here I will use IC. So, that means you can use any of the reference current notation, and then output of this comparator will go as an input to this particular latch circuit, and this whole logic is actually trailing edge PWM that we have discussed earlier. Okay? Because the switch turns on at the rising edge of the switching clock, and it turns off when the inductor current touches the peak current. Okay? And this logic we have also discussed, it is under trailing edge modulation and it is peak current mode control. But the same analysis what we are doing can be also applied for valley and average also. So, here IC is the current reference. Now, with closed current loop, if we draw the waveform, this is the current reference, right. So, we call this is the current reference, and this is our inductor current, the red one, and this is our duty ratio. Now, first thing, the assumption, the average inductor current is replaced by the control current. That means, if you go to the waveform, our initial assumption, suppose our this ripple is negligible. That means, suppose if our delta IL is very small than IL average, then IL average can be approximately replaced by this current reference. Okay? But in practice, this assumption, we will see in the subsequent lecture, will actually lead to that model accuracy of this model is not good enough when you slowly go to a higher frequency range. This approximation makes some sense in the low frequency range. This approximation also gives problem when we talk about modulator gain of the current mode control, but here we are not, and here we are also not considering any compensating rank. So, this model we are first no compensating ramp, ripple is negligible. So, the average current is almost equal to the current difference. But this is the starting point, remember. That means it does not mean that we want to limit our analysis. In fact, in subsequent lecture, we want to investigate the small signal model and we want to validate the time domain response of the small signal model with actual switch simulation. So, assumption here the average current is same as the reference current, the slope perturbation is neglected and part of current dynamics is this, and here no slope compensation is considered, no slope compensation, another part. That means, we are not adding any ramp with the inductor current. So, assuming negligible ripple that we have discussed. Now, if we start with this basic assumption, then we can see, we will see this circuit becomes very simple. How? So, we take a boost converter. We know all the equation of the boost converter, because we have already derived this equation when in lecture number 4 when we develop the MATLAB model. That means, the rate of change of inductor into L, that means this represents our VL, that is the inductance voltage. It is nothing but input voltage 1 minus Q into V0. That means, when Q equal to 1, the switch is on, this switch is on, this main switch is on, then the voltage across inductor is nothing but the input voltage. And when the switch is off, then Q equal to 0, Q equal to 0 when S on and S off. Then voltage across inductor is the input voltage minus output voltage. One thing you will observe, under when the switch is on, that means the circuit will be, the equivalent circuit will be like this, inductor current, inductor is simply shorted here and the capacitor will discharge across resistance. So, such scenario, that means as if we are getting two first order system, that means this first order system consisting of inductor, there can be parasitic resistance, and this circuit consisting of only capacitor. So, originally because of two energy storing element inductor and capacitor, it is a second order system, but for switch configuration 1, when the switch is on, two circuit get decoupled, that means inductor and capacitor get decoupled and it virtually looks like two decoupled first order system. And this is the problem of this boost converter, because in this configuration we have an input voltage here. Okay. So, inductor voltage across inductor is positive, okay, and if we continue this for long time, then the inductor current will keep on rising and at some point it will saturate the inductor, and that is the danger in the boost converter. That means, if you do not have control over current, if you do simple voltage mode control, and if you try to push the bandwidth high, it may so happen that during transient you can have a large on time, and that large on time can really increase the inductor current and it will never come back. And during this time the capacitor voltage will discharge, that means it will decay. That means, on one hand the current, in one hand the current will rise, and in the other hand, that means this is my output voltage, or under ideal condition the capacitor voltage will drop. It is continuously rising inductor current and voltage is continuously falling, and this is the reason, physical origin of non-minimum phase behavior, because here one state variable is increasing, the other is decreasing, even if you run it for long time. But if you take a buck converter, if you run it for long time, inductor is rising, and if you have a resistive load, then your output voltage will also rise, because your average, the capacitor current, because capacitor current is simply inductor current minus load current, and the load current, if you apply a fixed load current, okay, if your average inductor current goes above load current, so voltage will simply keep up rising. So, keep on rising until the output voltage becomes input voltage. Up to that point, voltage and current both will rise. That is why in buck converter you will not get any non-minimum phase effect or any right of plane 0, because we saw in the small signal model of buck converter, there is no right of plane 0. but in boost we got it, and the reason is this. That means, in mode 1 the two circuits are decoupled, but in mode 2, if you talk about mode 2, then the circuit is a parallel RLC circuit. That means, then in that mode 2 it is on and this is off, this is off, then it is a RLC circuit. In this mode there is no problem. That means, whatever energy is stored during the mode 1, that should get delivered to the capacitor as well as the load, right. So, we need to make a mechanism so that the inductor energy can transfer to the capacitor, otherwise the whole system will collapse and inductor will simply saturate and it may damage the switch, because the high current can exceed the limit of the devices. So, you have to be very careful about the boost converter, and that is why in most of the boost converter commercial product we use current mode control, where we have a direct control over current and we can limit the current and turn off the switch. So, here the switch we have a discontinuous mode. Similarly, you can the output voltage equation, as I told, if Q equal to 1, then C dVdt is equal to minus V0 by R, it will discharge. Okay, and input current in this case is same as inductor current. So, in contrast to buck converter, where we saw the input current is discontinuous, but in boost converter the input current is same as inductor current. So, if you take a larger inductor with very smaller ripple, then input current will be continuous, and that is why boost converter is used for solar application, where we want to draw a continuous current from the solar panel, because in buck converter we have a discontinuous current. In that case we need to put a capacitor, because the solar panel should not be exposed to the discontinuous current. But in case of battery charging or LED driving, where the load side we need a continuous current, where we generally apply a buck derived topology, where the inductor is in the output side. Okay. So, average current dynamics you can write, we already know that IL dt over a cycle. So, now earlier our dynamics of the inductor current was something like, just hold on. So, earlier we got the inductor current dynamics was V in minus 1 by Q into V 0, the whole thing by L, we saw. In this case, Q is discontinuous input, right? It is discontinuous input, it is a control input, discontinuous control input, and for such system this represents a switch linear system where you have a discontinuity. So, you cannot apply any Taylor series, because the Taylor series require the nonlinearity should be differentiable, right. That means, it should satisfy the Lipschitz continuity, but it is not in the current form when you have a discontinuous control input. But if we average over a cycle, then this Q, as if you are taking the average over a cycle of Q, then if you take the Q, that means Q, if you draw the Q waveform T, if you take the Q, it will look, it is a gate signal, right. So, if it is a periodic signal, okay, with a duty ratio D, so it is D into T. Now, if we take the Fourier series of this Q, that means if you take Fourier series, because it is a periodic signal, so you will get a DC component of the Q in the Fourier coefficient. If you take Fourier coefficient square, if you plot it, you will get a large spectrum at the DC component, and this corresponds to your duty ratio. Then you will get at switching frequency, then you will get harmonics and so on. But when we are applying averaging, we generally discard this switching frequency information. So, we want to retain within neighborhood of the DC average value. So, that is why if you take the average of this Q over a cycle in the conventional averaging, we are only taking the the zero frequency component, not the switching frequency component. So, in that case, this Q over our conventional averaging will simply become duty ratio, and we are replacing this average quantity. Similarly, we can take the average of the dynamics of the output voltage and average dynamics of the input current, and input current and inductor current are same. Next, once we apply the average, then you can see now all this quantity we can replace the average quantity, we can replace any average quantity is capital plus V in tilde. Sometimes we write tilde, in some reference book also we write hat. So, this represents perturbation. So, whether it is hat or tilde, this represents the perturbation. So, perturbation, that means if we replace this average inductor current, this quantity by IL, that means if you take ddt of IL plus IL tilde, then the derivative of the steady state quantity will be 0 and derivative of the perturbed quantity will be considered. Similarly, from this right hand side we will get a DC quantity and then perturbed quantity, and there will be a product of perturbed quantity which we will ignore. In fact, this thing we have discussed in the averaging technique, where we have considered Jacobian form or the Taylor series, and we have only considered the first order term, and with that we can write down all the perturbed dynamics here. That means, the perturbed dynamics of the inductor current, the perturbed dynamics of the output voltage, and here we have an inductor current average in a boost converter. Average inductor current is the average load current by 1 minus d, and average load current is, for resistive load, it is V0 by R. So, if you replace, then this equation can be written here. Okay. Now, we have two equations, the summary of equation, the perturbed current dynamics, inductor current, perturbed output voltage dynamics, and the perturbed input current dynamics. These three we require. Next, we have perturbed, which represents linear time invariant system, LTI, because here we have only considered perturbation and this linear time invariant system. Now, if we apply Laplace transform, then we can get S, all these things you can this if you take the Laplace transform of this, it will be S into ILS left hand side, then right hand side will be V in tilde S plus V0, this is a capital V0 steady state pointing to S minus 1 minus d into V0 tilde S. Okay. So, similarly, you can apply Laplace all these. So, you can apply Laplace transformation. So, we have three equations, number 1, number 2, number 3. Now, what do we want to achieve? We have fourth equation. What is that? That means, we have assumed that perturbation of the inductor current is equal to the perturbation of, because we have assumed the average inductor current should be same as the average. That means, what is our assumption? Our assumption was average inductor current was same as the average current difference, and if we consider the perturbed term, then average inductor current is same as average reference current, because their average quantities are equal. Next, we have to replace all this IL by IC, because we have considered this, right. So, it looks like the inductor current is replaced by a control current, and you will see the inductor will virtually become a control current source. Okay. So, if you replace in this equation IL bar, so input current, then we can obtain d hat from the current dynamics. That means, here we have three equations 1, 2, 3. So, if we take this and this equation 1 and 2, from these two equations I can all this, because it consists of input, output and all. So, I can get d0, or in fact we can use one of the equation, current dynamics. So, I can use this equation 1 and obtain d hat from this equation. So, we can obtain here and then replace in the input current equation. Since input current equation does not have any duty ratio, so it is simply the control current source. Okay. So, this is our control current source. Then next, we want to write the equation of the output voltage. What is that? So, output voltage we have an equation, and there initially there was a duty ratio term, right, duty ratio term, and we want to replace the duty ratio from this equation. And if you do that, then you can obtain this equation. That means, what does it indicate? We know C dV0 dt is nothing but capacitor current. So, we will call it, because the notation should be different, it is a capacitor current. And if we recall the capacitor current of a buck converter or any DC-DC converter, it has how many components? So, capacitor current, that means I am taking the capacitor current to be positive for when it is going in, because we need to give a symbol, sign, the direction of the current. So, I am taking the positive direction where it is going into the capacitor, because effectively it will charge the capacitor. If we take the positive current direction is out of the capacitor, then we need to take a negative sign here, because the capacitor will get discharged. So, here we are taking positive current direction to be going in. Next, this equation shows three things, and if you take the Laplace transform, what we will get? S V0 S is nothing but equivalent to I cap S, capacitor current. So, this capacitor current has three components. So, this you can treat like a constant coefficient into one current, right. Then you can think of this quantity virtually look like a, say you can see the dimensionally this represents current, because voltage by resistance and D is a dimensionless quantity. So, it represents current. Similarly, here also, but this term we can divide into two parts, minus V0 by R, minus V0 by R. That means, when you take the resistance which is in the output side, current is going, right. So, this I think okay, we will draw it here. That means, if we consider this current, what is this current? If we take this to be load current, so load current here is nothing but, now this current is positive, if we want to, and capacitor current is here. So, this is going out, that means in the capacitor current, if we apply KCL, the sum of this all current should be 0. So, this I told, this represents a positive current. So, it is added with the capacitor current, this is my I cap, it is added. Similarly, this is also positive quantity. So, this and this is replaced by f of C, this here, and this sign is positive. So, it is also added, that means it is going, it is contributing to the capacitor current. But these two are the one which is drawing current, and again the terminal voltage is V0. So, this quantity will be V0 by R, okay, and their direction, they are going out. So, there is a negative sign here, this negative sign because they are going, they are drawing. So, this represents the equivalent circuit where FC is here. So, this is my FC, I told you, okay, and you will see there is a right half plane 0 also, it is a transfer function, it is just not a constant quantity. So, overall circuit is this. So, this is my input current and it is coming out of the source, this is a control current. So, now you can see the input side current, the inductor which was there in the input side, it was there here, it is replaced by a control current source, and which is this, and it was inductor current. So, inductor current is replaced by a control current source, that means there is no inductor anymore, right. Output side we saw the circuit, and so we can get all this coefficient from here, right. Now, canonical form under current mode control. So, for this method can be applied to, we did it for a boost converter, we can do it for a buck boost converter, for a boost converter. So, we can, if we apply, then we can get input current. Similarly, the equivalent, so this is a generic representation, okay, and this canonical table, what are the values of this Fc, F2, this R1, then G1, G2, R2, everything is given in this canonical form, and for further detail you can refer to this book. Okay. So, this canonical model once we derive, because this already these things are discussed in well detail. So, I just want to summarize for part of model development in current mode control. So, for control to output transfer function of a buck converter or any DC-DC converter, ideal buck converter. So, if you go back to the canonical model, we have this one. So, if you take control to output transfer function, that means the definition means V0 to IC, which is my control current. In that case, we have to consider the input perturbation to be 0. Then what will be the equivalent circuit? What will be this circuit? So, this will be open circuit, right. So, it will look like this F2 into F2 into IC okay. So, this will be F2 into IC, then we have a emulated resistance R2, then we have capacitor and actual resistance. This is my load resistance, okay. This is my capacitor. That means, if I want to get V0, which is my terminal voltage, so it will be parallel combination of R2 CR divided by F2. That is exactly what is here. Oh, sorry, it should be multiplied by, because current is in the denominator. Okay, F2 into this, all these three, R2 R CS. Then for ideal buck converter, the transfer function is like this. So, it is just a simple first order model. Remember, it is open loop, but the inner current loop is closed. That means, your outer loop is open, because if you go back to the buck converter, what we did here, we have kept a current reference. It does not mean it is totally open. So, inductor current is forced to follow this reference, that is it. But we are not changing this reference as per the outer loop demand, because we kept a constant current reference. In that sense, it is open loop. Okay, and we are talking about the control to output transfer function. That means, a change in IC, how is it going to affect the change in output, and it turns out to be, it will be a simple first order system with a one pole for a buck converter, where in our original model of duty ratio control, direct duty ratio control buck converter, we have two poles, and that two are complex conjugate pole in general. Now, it becomes a first order system, and that is why we simulated buck converter without load feed forward. If you go to lecture number 17, you will find the response after load transient, it becomes very sluggish, like overdamped response, because it virtually behave like a first order system, because you have made the current to be a control source. So, there is the inductor pole as if you pushed it very far to the left hand side, that dynamics is not coming into picture. But another important point I will show you, what is the gain, DC gain. So, DC gain means you have to put it, that means you take GVC S and substitute S equal to 0, and you will get simply R. So, DC gain is a load dependent term, and you will see that is a major problem in current mode control. It has a poor load regulation. Okay, so, it is 1 by RC. So, the pole is 1 by RC here. This omega p is 1 by RC. Okay. So, output impedance, if we consider output impedance, we know the output impedance is, actually there should be a negative sign here. Z0 is minus V0 tilde by I0 tilde, where we are not taking this one, and we are also not considering, that means we are keeping the current reference constant, input voltage constant, but we are exciting the converter from external current source by sink currents, that means sinking current. Okay. Since the current is sinking, that is why the negative current, negative sign is coming, and this will behave like a parallel combination of R2C and R, and it turns out to be, for a buck converter, it will be simply this, and this is, that means in buck converter the control to output transfer function is virtually same as the output impedance with closed current loop with a constant current reference, that means with closed current loop only. So, it will represent a first order system, and output impedance in a current mode control also becomes a first order system like RC circuit. But in case of duty ratio control, we have an RLC circuit. So, inductor was there and we are getting a Q peaking effect. So, it was a complex conjugate pole, right, it has, and in that case we also got parasitic pole. If we ignore, there will be 1 0 at origin in case of an ideal buck converter, but in case of a practical buck converter, this is the output impedance. But output impedance is heavily dependent on the load resistance. That means, if there is any change in load resistance, your output impedance DC value will change, shift up and down, and that is why the major drawback in current mode control is the load transient load regulation problem, because we know that from the voltage source concept that we have discussed in lecture number 13, that if you have a output impedance which is load dependent, then you have real problem, because the regulation will be severely affected by this. So, in that case we can improve the load regulation by closing the outer loop and putting an integrator, but still the response will be very slow, because the loop gain will also depends on the load resistance. So, control to output transfer function of the ideal boost converter, if you take the canonical model, if you derive, and you will get the control to output transfer function, this is a constant term and one pole 1 0. The pole is 2 by RC, that means the boost converter originally in duty ratio control there are 2 poles which becomes now a first pole, 1 pole, because inductor is replaced by as if like a virtual current source. But what is important here is the location of the right, it has a right half plane 0, that means RHP 0. That means even with closed current loop we cannot avoid RHP 0, because that is the physical property of the converter. By means of control you cannot get it, maybe effect can be reduced, but in this case the location of the RHP 0 exactly same as direct duty control, direct duty ratio control. That means when you take the duty ratio control, when you talk about the control to output transfer function by varying the perturbation in the duty ratio. Here we have closed the current loop. So, one benefit we got, our current pole become a single pole, but you cannot avoid RHP 0, it is there. But at the same time, if you see the closed loop DC gain, it is R 1 minus D by 2, and that is the problem, because the closed loop DC gain, it depends on the resistance, and if you take this is for current mode control with closed current loop. In case of, that means no outer loop, okay. But if you recall the GVD of a boost converter, it can be shown that it is coming to be 1 minus V in by D square. This is for duty control, where it also depends on the duty ratio, but it depends on the input voltage. Here it is independent of input voltage, but it depends on the load resistance. So, the control to output transfer function of a buck boost converter can also be derived in a similar way, and you will also get a right half plane 0, and it will also have a single pole. So, the best thing about this boost converter, when you will design boost converter closed loop control, because the boost converter has in duty control has 2 pole which are generally complex conjugate and one right half plane 0, and the poles we will see, because of complex conjugate pole, it has a poor phase margin. and it also has a bandwidth limit due to the write up range 0. So, the boost converter has a real problem when you do voltage mode control, and that is why it is very hard to control boost converter under voltage mode, particularly when you are considering a wide operating range. But yes, in digital control the life will be much easier, because you have a flexibility to tune the controller. So, in ideal boost converter, buck boost converter, that will get the same RHP 0, but now the pole will be a single pole, and you will also have a load resistance dependent gain. Okay. So, audio susceptibility you can derive using the canonical model, but for a buck converter it turns out to be audio susceptibility 0. That means, it has no response in the output when there is a transient in the supply, and in fact, we saw in lecture number 17 with current mode control, when we apply a supply transient, the effect was almost negligible, but it does not mean that it should be exactly 0, there will be slight effect, but it is almost negligible. So, the current mode control inherently achieve very excellent line regulation and audio susceptibility. So, the boost converter again we can derive audio susceptibility, it is not exactly 0 for a boost converter. Okay. It has a pole effect. So, if you change the supply voltage for a boost converter, there will be some first order effect also. So, buck boost converter also you can derive. So, output impedance of a practical buck converter, one ESR will be added, and whenever you have an ESR with a capacitor, this will definitely introduce a 0, and that is exactly coming. Okay. That means, in some sense, suppose if you take a simple source, suppose this is one circuit, and if you take the output to this is supply, if you obtain the transfer function between V0 to Vs, you will get only single pole, no 0. But suppose if you introduce a resistance in between, and then you will get 1 0 1 pole. Okay. And that this is exactly is happening here. So, our practical buck converter also has a ESR 0 and 1 pole, and it has a DC gain of load resistance, and same as the output impedance. Okay. So, the DC gain is load resistance dependent. So, it is a pole load regulation, and this can be anticipated, though can be used as integral action, but whenever there is a large load step transient, the response becomes very sluggish, even though you put an integral action. So, in order to achieve faster transient, you may have to give a very high integral gain, but that is something not desirable, because that very high integral gain sometimes may saturate your compensator error amplifier. But the question, the approximate first order model, because there is no inductance like a double pole, so it is much easy to compensate. So, it is a robust. In fact, I will show you one case study. In voltage mode control, we can mathematically we can get a closed loop first order response, but that response is not valid even beyond a certain bandwidth range, whereas the current mode control, the first order response can be valid over a wide range, that also I will show. So, control to output transfer function of a buck converter ideal, and we can derive it, and we can derive for ideal boost converter the RHP 0, the load dependent DC gain, poor regulation, RHP 0 location same as both voltage mode and like a duty ratio control and current mode control, and trade off between RHP 0 and pole location better. This part will take up when we go to design of voltage and current mode, and we will see for voltage mode generally the cutoff frequency is kept RHP 0 by 5. This is for VMC. This is a standard kind of thumb rule, but we will come to through our analytical design process why it is so for a conservative design, whereas in current mode control it is F RHP by 3 may be a reasonable choice, and that also will come through analytical design process for a boost converter. So, we can get a better trade off or bandwidth using current mode control, but it cannot get rid of the RHP 0 behavior. So, with this I want to summarize the first order equivalent circuit model in current mode control was derived using circuit averaging technique. Effect on poles and 0 under closed current loop we have discussed, but the model validity with RAM compensation is a big concern, and we will see that this model will not be valid when you add RAM compensation and when both the inner and outer loop will start interacting this model. So, we need to go for improved model, and also the accuracy of first order model we need to investigate, because it looks really nice first order model, but I mean we can replace the inductor by a control current source, but we have to imagine even if you change a very fast load current reference, inductor will not respond immediately because it has a finite slew rate, and that practical effect as well as it will have some sampling effect will introduce some other behavior where we can improve the model accuracy by incorporating those sampling effect, by incorporating the modulator gain with RAM and so on. So, that we will investigate in the future lecture. So, with this I want to finish here. Thank you very much.